Now, hello.
Okay, now
check. Okay. Thank you. Okay, okay. So, remove this. Okay. So yes, one special thing that I want to say to you, which is part of our motivation, is that these jets are propagating at for very long distances from the central engine, which is with respect to the center, the jet is usually launched very close to the black hole, and the jet is at least propagating 10 orders of magnitude in centimeters. No, the first emission take place at 10 to 13 centimeters, and 10 to 16 is the second stage of this deceleration of these jets. So one of the challenge of this of modeling these jets is simulate self-consistently, with the central engine, the propagation of the jet. So the gamma ray burst has two emissions. The first one is called the prompt emission, and it takes place. It is properly the gamma ray emission, which lasts some few seconds. This is example of the Milky Way emission in gamma rays. When this burst takes place, it is shining, the entire sky. At least with respect the background, the gamma ray burst emission is 10 orders of magnitude greater than this background. So when this explosion takes place, it's you can see how it is shining, and the light groups also present a high variability, and also one mechanism responsible for this variability, it's the collision of the shocks. Well, the first blob emitted from this gamma ray burst jet is decelerating because the interaction with the interstellar medium, it decelerates before, and the material incoming from ejected from the central engine is colliding with the first shock front. So also, well, we have a plasma, and in this plasma we have if we are situated, if you are in the frame of the shock front, this plasma is compressed, and because the shock front conditions, you can amplify the density, for example, for 4 times the Lorentz factor of with respect the fluid rest in this interstellar medium, but also at the same time the magnetic field is amplified. In this plasma, the available electrons start to emitting in high frequencies, and one of the emission is gamma rays. Also, well, these explosions take place everywhere in the universe. They are isotropically distributed in the sky. And also, well, we have mainly 2 kind of duration of these bursts. Few of them last at least 1 second or less than 1 second, less than 2 seconds. But an important percentage of these events last also 10 or even 100 of seconds. And also these explosions are very take place very far away in cosmological distance. A second stage in the emission is the so-called afterglow emission. For do that, it's related with the gamma ray burst is usually detected by satellites. We have now mainly operating 2 satellites, SWIFT and Fermi. For example, this SWIFT is doing the orbit around the Earth. The gamma ray burst is detected, and it informs to the telescope on Earth what is the position of such burst. So telescopes in Earth in different frequencies, optical or even radio frequencies, and point to this source of explosion, and they can follow up the afterglow emission. No, the afterglow emission it's emitted in different frequencies, no, from X-rays and even in radio, no, and from the first days after the burst and even some months. One other thing that I want to say from this gamma ray bursts with and just for motivate the necessity to do numerical simulations, because the jets most of such events are observed on axis. So the source point, which is the jet head, it's the main source of emission, and since it is traveling at speeds close to the speed of light, the radiation is beamed. So you have only few geometrical region, no, to access to this information. So if you want to see or know what is the other regions of the jet is almost impossible, no. And also these events are not solved in the sky. These explosions, no. So we have only one off-axis GRB, but from the light curves we infer the properties of the jet. But there are some questions so still open. The main progenitors for this gamma ray burst are two. These jets are arising from binary neutron star mergers and from collapse of massive stars. Today I will focus on the GRBs originating from collapsing massive stars. In the soul of these observations, we have other rare cases in which the gamma ray bursts are also have a very long duration. Probably these bursts are coming from tidal disruption events, or we have other low luminosity jets which are probably produced by failed jets, and all others soft gamma repeaters what probably are produced by magnetars. So other well, this is observation of long gamma ray burst. And this is also one motivation that what we are interested in studying in detail, the hydrodynamics or the dynamics of these relativistic jets, because from the central engine we can extract, or we can obtain different kind of ejections. The relativistic jet, the cocoon, which is it's traveling, it's more slower velocities with respect to jet, but this is mainly created because the interaction with the jet with the progenitor star, and also a supernova is ejected from these massive stars. And every of the components of this fluid are responsible for emission. No, this paper is an example of the fitting parts of this for explaining these observations coming from different regions of the fluid. No? So more in detail for the formation of the GRB jets are here in this slide. First, well, also is this slide is I want to say something about the jet formation and our assumptions for these models, the models that I will present today. So we have a pre-collapsal massive star. This is typically a stripped envelope massive star, and probably lost the hydrogen envelope by high rotation. The nuclear reactions are already done in the center of the star, and the material is start to falling in the center. The first stage of previous to the jet launching is the creation of the protomassive neutron star. We have a high degenerated gas here. The magnetic fields are amplified to the high rotation of this at the same time magnetized gas start to accrete in this central object. And finally, we can obtain the collapsing of this protomassive neutron star into a black hole. It is a highly spinning black hole, and jet is launched mainly by Blanford-Snajek mechanism. We can see different cases in these central engines. We are thinking in three kinds of fluids, the high relativistic and midly relativistic ejections. One could be the case of the explosion of a supernova breaking the star, which is this case, and a jet propagating inside. And we could obtain a failed jet. It's just don't acquire the high speed velocities, or a jet crossing a supernova and crossing a star, or other case in which the jet is launched before and after that the supernova is launched. We can observe a failed, the jet is successfully crossing, the supernova propagating inside of the cocoon, or the other case, in which, this is the failed case, the supernova is in some way failed, but here we have two explosions. So one motivation is explore what could be the conditions to get these kind of explosions. Here I show an example on how these explosions can be modulated. But I want to say that these explosions are not self-consistent with the central engine, let's say, accretion activity. Here, for example, it's a work that we performed some years ago, where we impose by hand by strong jump conditions the jet, a successful jet crossing a star, which is this first column. And what is we perform the evolution of this jet during 300 seconds. Second one, how looks the jet crossing the supernova. The supernova was launched 1 second before, and the jet is crossing the supernova and after that propagating in the interstellar medium. So, and the role of the parameters in such kind of studies plays an important role, because we can regulate these parameters. For example, change the time injection. The time injection is related to how much energy we can extract from the central engine, for example. The total energy and the angular region where this energy is injected. So we can produce this failed jet. The failed jet is also, this jet is failed because it's not enough collimated to drill the star. So at the end, this material it could disrupt the star, but not. But the propagation is slow, and also the supernova. It is imposed as a thermal bomb, which a isotropic initial distribution of energy. These studies are mainly doing in two separate ways. The simulations of this kind of studies are very, very challenging and expensive, computationally speaking. So so far, the people have been studying the launching of these jets and supernova from collapsars, or from large scales. This is an example where we impose a jet very far from the black hole just to follow the propagation outside. But typically, these studies are not doing together, with jet launching and the propagation outside of the star. We'll do one or the other. But other recipients, things that we need to simulate this kind of, these environments has many physical processes. For example, the neutrino transport, which is responsible for convection in the first milliseconds when the inner layers are falling in the hypermassive neutron star. Or also how is the the evolution of the chemical components of the star. But this so far we are not included that because they are so expensive. But we are thinking in how we can, what could be the way to produce explosion just in the center and following these explosions outside of the star. So from some years ago, people had been studying the magnetically driven explosions. Previously, it had been demonstrated that if you start from a very, very magnetized core in the star, you can detonate an explosion. This is for, and this explosion could be ejecting jet, relativistic jet, but also relativistic supernova. This is one of the mechanisms to produce this superluminous supernova, for example. So, and also the time scales for produce these explosions are, I mean, these explosions take place very fast with respect to the previous one, no, that I showed. So we have a GRMHD code and thinking that we can produce these magnetically driven explosions. Just we can think, no, and how we can. Well, one of the main reasons, not also that, well, the main question that we have is from this kind of studies is just to connect the physics of the central engine with outside of the star, the things that are the observables that you can produce. For example, the history luminosity, how the luminosity is changing with time, the distribution of the velocities, the variability of the central engine, the mean lifetime of the progenitor, which is the time duration of the GRB, the jet opening angle, the final structure of the jet is related to the afterglow emission. So we can say something about the connection with the central engine at a very large scale dynamics. And also, one technique that we can apply here, numerically speaking, is the adaptive mesh refinement techniques, which allow us to follow in detail the propagation of the fluid to very large scales. The main idea here is just refine, I mean, the computational costs for do these simulations are related to how much fine is your grid. So the idea is refine in regions where it's important to and other regions like these, for example, in the center where the fluid is in frame does not take the resources here. Just improving where the resources you can invest the resources in which important regions. So also, well, how we can produce this kind of these explosions, very energetic explosions. So we can think in the following. Okay, these stars are rotating very fast and high spinning. And if you think in a very, well, the accretion is not in this way, but if you think in a spherical collapse, the first layers, which are the most dense, produce some change in the energy. Let's say we can see what is the typical accretion rate of this infalling material. And you can multiply the C square and get a rough estimation of how much energy you need to power a jet just for cross against this infalling material. This course, we have magnetic field, we have a high spinning black hole. We can extract luminosity via Blanford-Snajek process. So the luminosities that we need to produce are thinking in this typically accretion rates is around 10 to 52 ergs, and doing a rough estimation about how much you need for a magnetic field strength to power a magnetic flux. It's around in these typical values. These values are very high, but are still in the range of a magnetar. So we assume that previous to the collapse of this black hole, we have a protomassive neutron star which increase the magnetization of this region, and it could be explained this environment. Also, I want to say that in this work we are just one of the main goals is just launch the jet and disrupt the star, and just based it on our we are looking for what parameters produce the jet launching. We are looking for a reasonable or physical. I mean, not crazy initial condition for explain GRBs. So, well, for in these initial conditions, this numerical setup, we mainly play with two components. One is the structure of the progenitor precollapsar star, the progenitor star. We evolve our own star with MESA code. So here in this kind of simulations, we take care about the distribution of the density, because it helps us to magnetize the gas. And also we use the typical models, the Woosley performed by Woosley and Heger. These models are usually utilized in GRBs, in GRB simulations. So we impose a simple rotation and yes, different magnetic field strength from 10 to 12, 10 to 14 Gauss, and dipole geometry. So, and also for this study, we are performing 2D simulations. Just in the future, we are looking for explore 3D. So here in this panel, in this slide, I am showing 3 different panels. It's the same simulation. In the first one, I am focused in the central region. The second one is intermediate region. No, it's just beyond a little bit from the core of the star, and this is the boundary of the star. The jet is launched very fast in some fractions of seconds. We have this MRI explosions. The material is just here successfully crossing the most dense part of the star. And once the jet can open this central part, the jet funnel is already created, and it's more easily to continuously eject this jet from the star. We perform simulations around 7 seconds of evolution. This will follow until this jet is engulfing the star, and just for study as well the final distribution of the material of this star. So yes. Okay, here I want to mention something about the inner structure of the jet. We are focused on, as I said, in 2 different ingredients: the magnetization and the distribution of the structure of the progenitor. Here, for example, I am showing the same progenitor and with different magnetic field strength. And here I impose an hybrid geometry of the magnetic field, just to see what is the final jet propagation. And here we have these last 2 panels are referring to different star models. So yes, here is a slide of almost 4 seconds of evolution. And in the first panel, we can observe what is the implication of the magnetic field strength. Just it creates a structure of a jet, the typical conical jet, But while the jet is highly magnetized at the beginning, we can create these two sides of jet, the jet core, which magnetization rate is than 1, and some winds with some not much magnetized. But also we got this interesting structure where we with here the jet start with this simulation start with a magnetization of 10 to 12, and we produce a non-symmetrical jet. It's non-bipolar jet here, and it's not finished high magnetized as the others. The second one we produce with other geometry in which we combine a parallel magnetic field in the core of the star and a dipole outside of the core. This jet finish not magnetized, high magnetized, but with a cylindrical shape. This jet indeed didn't break the star, or at least in 5 seconds didn't break the star. And this other turbulent jet, which these jets are propagating in a different star progenitor. The shells of these stars has density jumps, and it produces more turbulence in the jet propagation. So we just for follow what are the implications in the future observations. We are study the accretion rate and how much magnetized finish this model. In particular, as is expected, the models which start with high magnetic field strength finish with high magnetic flux and less accretion. No, the highest accretion rate are such models which start with not magnetized gas or with few poor magnetized gas. Also, we are observing the jet luminosity by evaluating the 3 components of these fluids: the electromagnetic, thermal, and the kinetic component. So just to as well follow what is the dependence of the luminosity versus time, it can say something for the future observations of this jet, the history luminosity. But we get some interesting peaks in some models, which are corresponding to the jets that fastly reach the matte state. Well, we can see with the efficiency of the jet is just to evaluate with respect the accretion with the kinetic energy of the infalling material, and how much the jet is powered respect this accretion rate. We observe that the jets are some of the jets get very good efficiency in few fraction of seconds, and these jets fastly produce some explosions, no? And it is revelated by such peaks. In particular, we perform a set of simulations, but in particular, high magnetized, weakly magnetized, and not magnetized, just for also explored during large scales how these fluids are propagating. So yes, when we regulate the magnetic field, we are looking for what is the minimum conditions between what is the minimum magnetization for disrupt the star. So we produce this, for example, not magnetized ejection, just as a limit, but just for see how the progenitor is changing with the presence of this fluid and at the same time with the accretion. But yes, we observe that the funnel, for example, it's changing, depending of the magnetization. Let's say the jet opening angle will change or the mechanism responsible for the jet opening angle will see how magnetized these models are initialized. And also one thing that we are exploring, we are looking for how much time these models break the stars. Since we have very magnetized models, it explodes violently, and the most magnetized models break the stars in range of between 1 and 2 seconds. But one interesting thing is looking for a medium model, which explain with a weakly magnetized outflow, a model that can disrupt the star with a weakly magnetized initial setup. So here, for example, in this white line, we have the expansion of this outflow produced only by purely the accretion rate, the accretion process. But in some point, this shock front cannot disrupt the star because we have not a energy source activated here in the central engine. So here, for example, is we notice not the necessity of a central, for example, a central energy source at 1 second, which, for example, typically models that explain supernovas that has a neutrino transport can explain. When the accretion process is not enough to power this kind of outflows, it needed the neutrino flux for still pushing the material away from the star. But we have this weakly magnetized model where it's also traveling slowly, but in some point the flux is increasing, and the ramp pressure can be supported by the Poynting flux and finally break the star. Other thing that I want to say to compare, because we are looking for justify what we can observe at large scale and connect with the central engine activity, is just these flares, for example. We obtain models where these models are at the beginning saturated. The magnetization is high. And for example, well, this model shared the same color here. Here I plotted the energy fraction. The gross lines represent the kinetic energy extracted from these jets. And for example, the conversion to magnetic into thermal energy to kinetic energy take place very fast in the models that has these flares. The external layers of the stars, when the jet travel in the external layers of the star, it's just accelerated the jet very fast, and with the kinetic energy dominating, and it's almost ballistic. The propagation of this jet. And also one extra thing that we notice, which is always in discussion and in papers explaining GRBs, is the conservation of the jet opening angle, because the persons that are working with observations can do fitting with analytical models and looking for the jet opening angle. And but however, in some cases, it's not depending of the energy conversion. The jet opening angle is preserved or not. In some cases, the jet is recollimated. The jet opening angle was measured in 2 ways. With one of those is just how much is magnetized the jet is with this sigma parameter greater than 1. We measured that in 2 different regions, very close to the black hole at 15 gravitational radius. And the second one, how finish the magnetization just when the jet breaks the star. And this with this magnetization criteria, sometimes it's not preserved, the jet opening angle. But since we have conversion to kinetic energy, we also measure by we define the jet opening angle with the regions that have the most speed or the highest high velocity material, and with a for velocity greater than 2, just to check if it is corresponding to the jet opening angle at the beginning or in the base or close to the black hole. In some cases is preserved, but in the models where I will show because it is more explained with the jet structure. Here we can see where the energy is isotropically distributed and when not. Here, for example, I have this two comparison is curious because here I started with a initial magnetic field of 10 to 13 Gauss. Our MESA model, which is has a uniform core at the beginning. How this is yet the magnetic flux is amplified in the center, and we finish with the magnetic energy. I am presenting the different components of the energy: magnetic, thermal, and kinetic. The magnetic energy is dominant here in the poles. But for example, in this star, which this 16 Ti star has a very steep core. The high density is concentrated very in the core of the star, and after that, the other layers decline very fast. So at the beginning, the jet cross this very dense star, but fastly the magnetic energy is distributed, in thermal and kinetic, and finally this jet finish almost isotropically. So we determine here that the most important ingredient for produce the differences in observations is the structure of the star. Here we estimate light curves from our simulations. So, but here these light curves were estimated analytically, by the synchrotron emission. We assume we have a computational box which finish at 10 to 11 centimeters, but the afterglow emission is starting to at 10 to 16 centimeters usually when the jet starts a deceleration state. So we use the Blanford-McKee model here and the synchrotron standard model for GRBs. Just we follow how we assume that the distribution of the energy and the material is the same after this region, just a similar evolution. So, and we explore both on axis. We cannot see huge difference. This is the most boring way to see, to compare GRBs, because we can see only difference in the flux. The flux is related with how much the jet, how much power was extracted from the central engine. But the interesting parts are of axis, when we can see at least a difference. This bump, for example, which is related to the structure of the jet. This bump is because the signal of the core, the high collimated jet, which after have some delay to the observer at 30 degrees with respect the propagation of the jet. So yes, I want to do the summary of this work. We we perform simulations of jet launched from the black hole and crossing the boundary of the star. It was the main goal of the of this work, just producing simulations, or our setup is able to perform this model. We are producing jets from magnetic field strength starting from 10 to 12 Gauss. We obtain luminosities in a range of 10 to 50, 10 to 53 ergs per second, which are typically in GRBs. Our maximum limit is have a magnetic field strength of 10 to 14 Gauss. Well, depends of the magnetization. We can change the structure of the jet, but the progenitors, the star profile is the most important ingredient, or the ingredient that impact strongly the final jet structure of the jet. We have some limitations for this study. It's only 2D. But we are looking now for perform 3D models. Also, we don't have radiative transfer, but soon new work is coming just for solving neutrino leakage, for example. And also, I want to say that the evolution of the black hole spin here is constant, but also my colleague Piotr is working on that. So thank you very much for having me, and thank you.
This is time for questions. If you have any question? Yes.
I have a question about the jet luminosity. It means you have no radiative transfer. It means kinetic luminosity also.
Yes. Only we evaluate the energy components. I mean, the luminosity as the Curly way, no, which is the flux crossing a surface. Which yes, the magnetic.
And the kinetic or other?
Depend of the model. In some models, it's dominating the magnetic luminosity. In other models, kinetic. Indeed, the kinetic luminosity is dominating here in the models that present these flares. Yes, I didn't mention, but this luminosity, I measured the luminosity close to the black hole and outside of the star. This is the luminosity just evaluated outside of the star. Yes, here, for example, is dominated. The kinetic luminosity is dominated. Here is still dominating the magnetic one.
And this magnetic, it means that magnetic flux dense, no, magnetic field density and how it's propagate or something.
I think here I added the equation. Is this just the component? Yes. Here, yes, the magnetic luminosity is the component of the magnetic field. Yes, the flux, basically the magnetic flux, and the thermal one is just the pressure in the flux, and yes. And for the afterglow emission, there we assume that the kinetic energy is. I mean, we assume that in this case the luminosity all is kinetic. We assume that 10% of the fraction of this energy is power, the flux there, and 0.01% is the 0.01 fraction is the contribution of the magnetic energy.
Okay, more questions? I have the question. Do you consider, do you assume some type of the progenitor stars or?
Yes, the stars which are around 40 solar masses before the collapse.
The stripe stars.
Yes, the strip envelope stars. Yes, mainly some Wolf-Rayet type stars.
I have one controversial question. Do you can imagine that fake supernovae with the gamma ray burst emission, or this is completely impossible?
When the first collapsar model was called the failed supernova, no? But you mean?
Yeah, you have like the failed jets, but in just the opposite situation. You have the collapse and you have the jet, and there is enough energy to have the eject of the rest of the mass, or the accretion is so efficient.
Yes, in some cases, but yes, well, every fluid is possible to produce, but yes, just you need to looking for the bridge here, no? A bridge where the thermal component is important to power it. The fact is just power this shock front, the ramp pressure here, and which energy source you have. But yes, I think it's possible. But the transient, I don't know which kind of transient, no?
Do we have any question from audience on Zoom? Okay, we have no question from Zoom. So let's thank Gerardo again.
Thank you.
Good morning.
Thank you. Thank you for the invitation.